Good morning, everyone. Welcome. I am joined by my colleague Daniel Moyer today. My name is Nathan Heston. Both of us are technical trainers here at Briggs & Stratton Energy Solutions. And we'll be presenting to you on the topic of AC and DC coupling. So the title of this talk is Unlock a New Customer Base, Learn How to AC Couple Batteries to Existing Solar. Couple of things as we get started here. There is a Q&A feature that you should be able to find on your Zoom window. Go ahead and pop questions into that, and Daniel will be monitoring that. Additionally, there are NABCEP credits associated with this talk, so if you're here for NABCEP credits, please stay through to the end. Daniel, how are we doing on attendance so far?
We're good. We got some people joining us, so thank you, everyone.
Wonderful. So we'll go ahead and get started right at the top of the hour here. If you are interested in trainings, and it appears that you are since you're at this one, we do have some in-person trainings coming up. I will be heading up to Santa Cruz, California this Thursday to run an in-person training. We still have seats open in that class if you're interested in an in-person training session together with us and representatives from Solarc. So that's this Thursday. And then next week we'll be in Glendale, Arizona, right next to Phoenix. And we'll be running a training there at Gentech. So
and we're going to have real product there, right, Nathan?
Yeah, we'll have rail product at both of these. Yeah, so thanks for mentioning that, Daniel. We'll actually have a training wall, and we'll do demonstrations of installations of the batteries, as well as the wiring of the inverter, etc. We'll be able to point out how a real system would look like, so appreciate you mentioning that. So if you're in those areas, feel free to come join us. These are free trainings, you get a free lunch, and a great view of the product itself. So the latest product from Simplify is this stackable battery, which I'm sure you've heard about already by now. It's a 6.6 kilowatt hour stackable module that goes together into stacks of up to 3 batteries, so 20 kilowatt hours. Has closed loop communication pairing with Solarc. It's indoor and outdoor rated battery. And one of the things that is a notable feature about our partnership with Solarc here is the fact that we're two American companies. Two American companies coming together to give you good quality technical support, good service, excellent service, and we've been around for a long time. I note that our warranties, right, they're backed by long-standing U.S. companies. Briggs & Stratton is a 115-year-old U.S. company. So we're there for you. And we're looking forward to introducing you to this product if you have not installed it yet. In fact, we do have a promotion out there, which I'll mention at the end, but you can get $1,000 off your first Simplify 6.6 stackable ESS system. We also have packages that we're offering with these products. I'm not going to spend a lot of time on these packages, but these packages help give a homeowner an estimated amount of backup time. And of course, everything can be customized with these systems. We are going to focus a bit on the Solarc 15K just because that's the most common inverter used in our installations, but this training with AC coupling involves other inverters, and of course you can carry these lessons to the inverter of your choice. We have other closed loop communications packages kind of on the way. Those are not completed yet. You are welcome to use the 6.6 battery or any of our batteries in open loop mode with other inverters as well. So today's training is going to focus on AC and DC coupling, understanding the difference between the two. And this is applicable to retrofit systems where an existing solar array might already be on the roof. But those existing solar arrays that are grid-tied arrays don't offer any backup in the event of a grid outage. And so as NEM 3.0 decreases the value of feeding energy back to the grid here in California and feedback incentives reduce around the country, we're seeing more and more self-consumption. And in order to do self-consumption effectively, you'll need to have a battery. And that battery can either be DC coupled to the solar array or AC coupled. And one of the focuses of this talk is to understand the difference between the two. We'll talk about some of the highlights of adding battery backup to AC systems. We'll talk about some best practices related to sizing AC systems to batteries. You want to make sure you have enough available charging capacity of the battery to take that full power of the array in a grid down situation. And we'll also talk about how to use batteries to maximize solar production and optimization. We're going to start first at the basics of what an ESS is, and then we'll point out exactly what we're talking about with AC coupling. So an energy storage system with solar typically reflects the inclusion of a battery system, right? So energy storage here means that there's a battery capable of storing that energy that's coming from potentially a solar array. It could just be coming from the grid and charging that battery, or it could be coming from a generator. So at the heart is a high-end battery like the Briggs & Stratton stackable battery that you can see there. An inverter is also needed to transform the DC power from the battery into usable AC for AC appliances in the household, or to sell that extra energy back to the grid if you're using solar and you have an interconnection agreement. With AC coupling, what we're really looking at is the connection between the AC solar and the battery, right? So you could have a system on your roof where the solar panels are potentially connected together in this string and running into an existing inverter on the home, or those panels are connected to microinverters, and those microinverters are feeding AC back into the load center of the house. So when we're talking about AC coupling, we're talking about the relationship between the inverter that's connected to the solar and the batteries. So some key terms here, coupling in context of PV systems. So what we're talking about is how the solar panels are coupled to the battery bank. So when we refer to AC coupling to energy storage, what Daniel and I will mean in this talk is coupling AC power from inverted PV array that's going to be converted to DC power by a battery charger. And that means taking that existing solar, which already has either a stringer inverter or microinverters on it, running that through an inverter that's capable of charging a battery. So in the previous example, I showed this being done with a solar converter. Not all inverters are capable of operating with batteries. And even some inverters, some very popular inverters like solar edge inverters, are capable of using batteries, but they're not grid forming. What does that mean, Daniel?
Essentially, that means, right, if you have a system that's grid tied, these microinverters or even string inverters are designed to shut down in the loss of grid, right? You don't want to be backfeeding the grid if there's a loss of utility, right? Backfeeding the grid is dangerous. Some linemen down the road trying to get the power back on. What these grid forming inverters can do is disconnect themselves from the grid and then essentially create a grid that's suitable for those AC coupled microinverters or string inverters. They don't see any loss of the grid, and essentially you're providing a grid in the home. As far as those micros or that string inverter is concerned, it's just the grid, and it's going to continue to output.
Thank you, Daniel. Yeah, so a typical string inverter system or microinverter system, a grid-tied system, will shut down with a loss of grid. And so if you have a grid-forming inverter, you can keep that system on even in a grid outage, which means that solar will be there and available to charge the batteries. So not just will you have your batteries to back up your power of your home, your backed up loads during a grid outage, but you'll also have the solar to recharge those batteries as long as there's excess solar. DC coupling to energy storage. So coupling DC power from a solar array through a DC input battery charger in order to charge a battery bank is typically what we're going to refer to as DC coupling. So this is coupling without the use of an intermediary inverter like a string inverter or microinverter, right? This is basically taking the DC directly from the solar array, bringing it through some MPPTs, and charging the battery. All DC to DC conversions taking place there, which is much more efficient.
You
And
know,
AC coupled batteries. Yeah, go ahead.
Nathan, you mentioned PWM charge controller, pulse width modulation charge controllers, and those used to be very popular. But what I've noticed, and maybe you've noticed in the industry, is the cost of the MPPT charge controllers have come way down, just
Yes.
like a lot of the other components in this industry. So I don't see them very often. And if anybody is still using PWM charge controllers, please let us know in the chat. We did have one question, Nathan.
Sure.
Um, when commissioning, will I be able to keep battery from sending power to utility? I understand it does that during grid outages, but what about regular usage? Inspector mentioned this as being a concern.
Yes, absolutely. So depending on which inverter you're using, that inverter does need to disconnect from grid during a grid outage. And I thought the question was, can I prevent the battery from discharging to grid during grid outage? That is a necessity. That's called anti-islanding, and you'll certainly be able to prevent that. But with most software, especially with the Solarcs that I'm going to be mentioning, you can prevent the battery from being discharged back to the grid. The AC coupled solar will need to be fed back to the grid if you're to keep it on. So any excess solar with AC coupled solar is typically fed back to the grid. And if you want to bring AC coupled solar into a Solarc, you will need to have an interconnection agreement with your utility in order to export that excess power.
And that's a good difference there, Nathan. You mentioned from the solar to the grid, but the battery to the grid can be curtailed.
Yes.
And there may be situations where you do want the battery to go to the grid, but again, that falls under some of the ITC requirements that you have to charge the battery from the grid. I mean,
Yes, and you do
from the
have
solar.
independent control of both of those two different things, the battery feeding to the grid and the excess solar feeding to the grid. So let's talk just briefly. I kept this slide in here so we could talk a little bit about what happens inside a solar panel. So solar panels or solar modules are composed of many individual solar cells. And essentially when sunshine lands on the top layer of that solar cell, it forces electrons down into a lower layer. So there's a very small p-doped layer of semiconductor on the top of a solar panel right beneath the glass. So when sunlight comes down and hits that, it actually makes that solar cell act as like a little electron pump, and it pumps those electrons down, and they get collected by the nickel strips. And then those cells are all connected in series. And so you have a flow of power from the top. You have a flow of electrons from the top of one cell down to the bottom. And those are connected with these nickel strips. And then in series, it comes to the top of the next cell. And those electrons get pushed down through that cell, et cetera, et cetera, et cetera. And so you end up having all of these cells on a solar module, or most of the cells on solar modules are connected in series, unless it's a split panel. And so if any one of those cells gets shaded, you can limit the power output of the entire solar module. And in fact, if you have many modules together in a string, you can have power output limitations due to shading of a single module or even part of a module. And I've seen that in the home solar array that I had in my house. And that's one of the arguments that companies like Enphase with microinverters or SolarEdge with optimizers makes about using their optimizers or their microinverters. And they say in shaded conditions, microinverters and optimized string inverters are more efficient, and that can be true. And so if shading is a common thing, AC coupling with microinverters might be a better option for the solar array. So each solar panel on an array has a label on it that might look something like this. And I'm not sure if this is a real array or just a simulated one. I pulled this one from the web, but it has different numbers on it. And these numbers correspond to the outputs of the solar panel. And they're typically the outputs of the solar panel under standard temperature and irradiance conditions. These are standard test conditions. Typically, it's 25 degrees Celsius. It's AM 1.5, which stands for air mass 1.5. It's kind of the angle of the light, the sun coming through the atmosphere. So there's some filtering to the light that happens there. And you get about 1,000 watts per meter squared under those conditions. So the output of a solar panel is by no means 120 watts just because you have a label on the panel that says 120 watts. It depends on many things. It depends on temperature. It depends on the angle of the sun that's coming. It depends on the intensity of the sunlight that's there. And so typically, Daniel, current increases with the sunlight, right? What are other factors that can affect the current?
Well, the temperature, you hinted at that, the temperature of, and under standard test conditions, they're testing air temperature, whereas there's other test conditions that will measure cell temperature. And as the temperature of the cell decreases, voltage will go up, increasing power output. And conversely, if the temperature goes up, the voltage will drop.
Right, so there are factors that affect the voltage output of a panel as well as the current output of a panel. There's a fairly large effect. I mean, a large effect by meaning a couple of maybe 5% or something on a cold day, you'll see an increased voltage of your array. But there's also a small effect of the temperature on the current output of the panel as well. That affects the resistance of the cells themselves of the semiconductor and in the nickel strips connecting. So you will see variable output, and typically the way we maximize the output is through an algorithm where we vary the current that we pull from a microinverter or an optimizer. And by varying that current, we can vary the voltage output. And under standard conditions, you might see a curve that looks like that red curve on the screen. The product of current and voltage is power. And so what we're really doing is trying to use our equipment to pull the most amount of power out of the solar panel as possible. If we pull too much current out of the solar panel, the voltage will go to zero. And if we don't pull enough, we'll be saturated in voltage, but we won't have much power. And so there's this point called the maximum power point. And those are the values that are labeled on your panel. If you want to look at the most amount of current you can get through a panel, it would be the short circuit current. That's when you would that's the current that you would get if you just shorted the positive and negative leads of the panel together and it just pumped electrons in one big circle. So that's your short circuit current is the most current you would get out of a panel, but the current you would get out of the panel during a maximum power point is slightly reduced from that. And the voltage that you get out of a panel, if you're not pulling any current from the panel, that's your open circuit voltage. But under standard operating conditions, you'll be operating at a slightly lower voltage called the maximum power point voltage.
And those voltages are important to keep in mind, especially in context of DC coupling. A lot of these maximum power point trackers have certain voltage ranges, so you need to wire enough modules in series to build up the voltage so that you're above the MPPT startup voltage, but not exceeding the maximum voltage that MPPT can handle. I've also noticed, Nathan, that these ranges are getting much larger. Some of these MPPTs can go up to almost 600 volts now.
Yeah, and the Solarc that we'll be talking about, the operational voltage is up to 500. The maximum open circuit voltage of your arrays on the 3 MPPTs is 550 volts. Some of the smaller charge controllers that I'll show here in a minute have lower overall string voltages. And so let's talk real quickly about combining solar panels to form arrays. So each individual module has the characteristics we gave before. So I am showing you a picture of a real solar panels label in the top right there. So if we combine solar modules together in series, then the voltages would add up and increase. If we combine solar modules in parallel, meaning we connect the positive sides of both panels together and the negative sides of both panels together, well, our currents would increase. It would be the product. It would be the addition of those two currents, but the voltages would be equal. And typically, solar arrays are connected either in a string of single panels or maybe a couple of panels in parallel and pairs in a string that's in series. So, for example, let's suppose we had a connecting device which had a limit of 300 volts input and a maximum of 30 amps of maximum power point current. If we use that panel in the top right corner and we wanted to have an array that would fit that, and we had 10 panels, we couldn't just connect 10 of them together in series. If we connected 10 of them in series, our maximum power point voltage would be 407 volts. Our open circuit voltage would be 494 volts, way too high, right, for this 300 volt limit. But what we could do is we could put two panels, we could connect pairs of panels in series. So we could split the 10 panels into 5 groups of 2, and then join them that way. And that would be a 2P5S configuration. Then we'd be looking at a short circuit current of what 2 panels would produce, and an open circuit voltage of that voltage coming from a series of 5. And that would match our charge controller there. Other ways to join panels is through the use of DC optimizers. And so DC optimizers can essentially isolate and optimize panels even on a individual level. Or we could connect paralleling panels through the use of microinverters where the DC is directly converted into 240 volt AC. This is more what we're going to be looking at today, the latter 2 examples where we're looking at DC optimizers coming into an existing system. This is very common with SolarEdge, or microinverters on individual panels or pairs of panels converting directly to AC.
I love that you're still showing the math, Nathan. I think we get reliant on Open Solar Aurora, where you string together the solar panels based on the device, and it will tell you if you've exceeded the certain limits. But I think fundamentally understanding the math behind a lot of this is key to the concepts that we're trying to get across today. So thank you for showing that.
Appreciate that comment. All right, so what we're looking at here, and I'm going to talk to you a little bit about the market share that Enphase and SolarEdge, those 2 examples I just gave, has. But what we're looking at here is an array being prepared to go on a roof in which we've got Enphase. Those look like IQ8s. And those are Enphase microinverters where panels will be mounted over the top. And you can see on each of those microinverters that you've got an input for your MC4 connectors from the panel. So each panel will plug directly into one of those microinverters. Those microinverters are going to be all paralleled up at 240 volts AC.
With the trunk cable.
Yep. And those will be combined into strings, but slightly different strings from the DC types of strings, right? Strings of panels that were paralleled. And so those currents will add up. And then you'll have a combiner box typically down on the side of the house. So what you're looking at here, I see a conduit drop coming down, and then those strings coming into looks like 2 inputs, 2 strings here. And then so this is the Enphase combiner box, and this is an AC disconnect, it looks like here. And then that power will be sent from that AC disconnect into the load center of the house. If there's excess power, the excess power will flow back to the grid. Here is an example of a SolarEdge system with DC optimizers already on the roof, ready to have the panels plugged into them. These optimizers will work differently than the Enphase microinverters. These will keep the power DC, but these have DC to DC converters in them and essentially act fairly similar to an MPPT, a maximum power point tracking device. And you can see that power coming down the side of the house. This looks like a SolarEdge 7600, and that's got a disconnect. And those optimizers also act as rapid shutdowns in the same way that the microinverters you saw here will act as rapid shutdowns. So unlike with a DC, unlike with a DC system where you just have solar panels and you're required to have accessories as rapid shutdown devices, both of these sets of devices will work as rapid shutdowns in the event of a grid down situation.
And that's been a critique I've heard of DC coupled systems, is that you got high voltage DC coming down off the roof. And that was true before the requirement for rapid shutdown, where now you're required to either use optimizers, micros, or rapid shutdown devices that will disconnect on the module level that high voltage DC coming off of the roof.
And these changing requirements, Daniel, are exactly why you might want to AC couple a system, right? You might have a system that has already gone through permitting, is operating completely fine, but the customer wants a battery. They want an integrated battery. They want to have backup because they're getting frequent outages. And in order to do that, you could AC couple to an inverter.
Don't
So,
even get the ladder off the truck.
yep, without even having to go up on that roof at all. You don't have to remove those panels. You don't have to change the configurations on the roof. We can AC couple. So before I jump into AC coupling, I'm going to talk just briefly about charge controllers. This is a typical DC coupling thing. And you might see this more with off-grid systems. These things are becoming less and less common, especially as solar has gone mainstream. But Daniel, you mentioned PWM controller. You can get these controllers for about $11. You'll typically see these on very cheap, experimental home systems. I haven't seen any on more serious systems. But as you also mentioned, the MPPT charge controllers have gotten cheaper. So the charge controllers have gotten more sophisticated and cheaper, and many of them are integrated into hybrid inverters. But you can use a charge controller to directly provide power from a solar panel to a battery system without any inversion, right? Just keeping the system entirely DC. And a PWM controller can do this. You'll typically have higher voltage coming off your solar array, and your charge controller needs to turn that high voltage DC into a voltage that a battery would accept. So for example, you might have a 40-volt solar panel on your roof, but you might be charging a 24-volt battery. The charge controller is responsible for reducing that voltage. A PWM charge controller can do that through the application of what's called pulse width modulation. So what it will do is it will provide, over a very short time scale, we're talking milliseconds, it will provide short bursts of 40 volts and intermixed with 0 volts. And that average voltage over that short time window would come out to be, the voltage required to charge that 24-volt battery. So this is known as pulse width modulation. I probably could have done a more elegant way of explaining it, but it is somewhat complicated.
Well, a lot of times when we use these, Nathan, we would have 36 cell or 72 cell modules. So we get pretty close, 18 volts for a 36 cell module, close to that 12-volt battery that we're typically charging up. With the MPPTs, and I think you're going to get to it, we can use much higher voltages, series connections, and avoid all those parallel connections. We do have a question.
Yes.
Keep them coming, everyone. When AC coupling to existing solar, do I need to check if the person who owns it, if it's a leased system? Can we add a battery to a leased solar system?
Well, that's a good question. I would really defer to you on
Yeah,
that,
and I would
Daniel.
say no, you cannot, because these leased systems, right? The homeowner doesn't own them. What they're doing is that they're entered. Well, at least maybe, and again, whether you have a loan and a lease is a little different, right? If you have a loan, you can, right? Because you're just paying it off. But if it's leased, you probably have somewhere in the contract that you're expected to export a certain number of kilowatt hours to a system, to the grid, or to make those credits. But again, if you start to add batteries, all of a sudden now you can store that energy on the home and discharge it to the home's load. So yes, absolutely check that. And the homeowner may need to have to buy the lease out in order for you to add that. A loan, you're good. Of course, if they own it outright, you're okay.
Okay. And I included this picture of this sun saver because Daniel, I know you like it. This has a DC load output on it. So typically, with the systems that we have, because all of our appliances are AC, typically we're looking at charging a battery and then having an inverter.
Well, it has a low voltage battery disconnect, which is really why I like it.
Okay. All right, so let's look at the more common MPPT and what a MPP charge controller does. And these are typically incorporated into hybrid inverters now. And the Solarc that's shown there, that's a 15K Solarc. It's got 3 MPPTs built into it. Each one can take 2 strings of paralleled solar. So you can bring a lot of solar in, and that charge controller is built into the inverter itself. So many of the hybrid inverters don't need an external charge controller. A notable exception, right, is the Schneider inverter, right? That Schneider inverter does require a separate charge controller. What you're looking at there is Midnight's one of the Midnight charge controllers. So what does an MPPT do? It takes a string of solar that's coming into it, typically at high voltage, and then that charge controller maximizes the output of that solar array, but then converts that output to the charging demands of the battery, right? And so if you are using an independent MPPT charge controller with one of our batteries, do make sure that you can use the appropriate 3-stage charging and meet the LFP set points. Most newer equipment on the market certainly can do that. But if you're going to use legacy equipment, make sure that it's compatible with LFP. And inside those charge controllers, they have a DC to DC converter that regulates the battery charging. Like I said, most inverters, most hybrid inverters now that are compatible with batteries come with built-in MPPTs. Here's an example of a system that doesn't with Victron. I included this just because it's such a simple example. So you've got your solar power coming in. It goes through an MPPT, which maximizes the power that the solar is producing, puts that onto a DC bus where your batteries are in parallel. And that the voltage of that DC bus is controlled by the charging circuitry that's here. So if those batteries are 48-volt batteries, we'd have 48 volts or greater to charge those batteries on this DC bus. And then the inverter here can pull power off that DC bus, both out of the solar and out of the batteries, right? It can pull power off that DC bus, use that to power loads in the home, or send excess back to the grid. So that's typically what's happening inside most hybrid inverters. Here's an example of a hybrid inverter that's DC coupled. So we've got solar panel coming in. These are not micro inverters here. These are rapid shutdown devices. Those are AP Smarts, Daniel?
Yeah, and those actually can connect up 2 modules per device.
Yep.
They do
And
sell
so,
singles
yep.
as well.
Yep. And an alternative popular brand is the Tigos, right? And you do need, I don't show a transmitter on here, but there's a transmitter required, an external transmitter for the Tigos. And depending on how big your solar array is, you might need more than one transmitter for your system. This DC solar is then fed through a disconnect into the Solarc. There's a rapid shutdown button there, and that Solarc can use this DC power to either charge the batteries, or if the batteries are full, send that solar power out to the loads of the house, or if there's excess, send it back out to the grid. And we're also showing this Solarc together with a generator that's there for a grid down event. So
one comment. I know, Nathan, go back one slide. I know we're coming up halfway through, but you show a 40 amp breaker going to that. I assume that's a 200 amp, 200 bus main load center there. We're showing 50
apology,
loads
that was supposed to be
critical.
a 60 amp for that solar.
And why can we now put a 60, right? The 120% rule isn't really a factor anymore. Why? Because these inverters now have power control systems, right? They can still draw 60 amps off of that main panel, but they're never going to send back more than what you program it to. So it's really exciting to see these new PCS controllers coming into effect with UL listings that now allow us to upsize and not really follow our 120% rule, which I think is really benefiting the DC coupled architecture.
Yeah, it allows you to pull more through that inverter than pushing back. So you can limit the amount you push back to the grid, so you're not breaking the 120% rule, but you can still pull the 62.5 amps is what that breaker should be. And I do remember changing it, so I must not have saved that change. So I wanted to put this comment out there. There are a lot of existing solar arrays on the roofs around me. And I Googled trying to find what the market share was between SolarEdge and Enphase. And this is a long time ago now. 5 years in the solar world is ancient history. But in 2019, SolarEdge and Enphase had 80% of the residential market in the US. So the majority of the arrays on the roofs of houses that you see, right, are SolarEdge and Enphase. Back then it was 80% of the market. So more recently, I found an article that says it's now 80 or 95% of the global inverter market share, and it's 88% of the US market share. Enphase holding 48% of that, SolarEdge still hanging on to 40%. So it's a very large fraction of the solar arrays you see on the roof are already up there with probably functional existing microinverters and DC optimized systems. And one of the things about the SolarEdge system is that the DC optimizer will not work without a SolarEdge inverter. So they essentially prevent you from using that DC power coming out of the solar arrays. You can't use the optimizers if you don't have the SolarEdge inverter. So if you wanted to convert that SolarEdge system to DC coupled, you'd have to get up on the roof. Well, first you'd have to do all your permitting, then you'd have to get up on the roof, replace all those DC optimizers with rapid shutdown devices, redo your wiring, come back off the roof, and bring that into your new inverter if you wanted to swap that inverter out. But an easier way to do it would just be to AC couple it. So here's an existing grid-tied array, fairly simple diagram of a grid-tied array here. We've got solar panels. Each of the solar panels are plugged into microinverters. Those microinverters are coming into a combiner box. We've got a DC disconnect there, and we're going through the SolarEdge monitoring and control system, and then into the load center of the house, where that 120% rule that Daniel mentioned is in effect, right? Because you're feeding all that excess power onto the AC bus of the load center. Daniel, you look like you wanted to make a comment here.
Oh, that's an AC disconnect, Nathan.
Oh, okay. Sorry. Yes. Thank you. All right. So I'm showing an example. Okay, here's where I've actually got the amperages correct. So here I'm showing an 8K Solarc, and we are AC coupling that microinverter existing solar into this 8K Solarc. And in a grid down event, what would happen normally for this array before we made the change to a Solarc with AC coupling is that the whole array would go down. So in a grid outage without the Solarc there, the Enphase solar array provides zero backup. But by bringing in a Solarc inverter with Briggs & Stratton batteries here, what we can do is we can keep that solar on by grid forming. And so what happens is that in a grid down event, the batteries can be drawn on by the Solarc to provide backup power to the critical loads of the home. And that signal from the Solarc, the power the Solarc is producing, looks like the grid to the microinverters that are on the roof. That turns them back on, and they start pumping power. In the event that that battery fills up and that the loads of the house are not consuming all of that power, we need to be able to shut that power down or reduce that power, and that's done by frequency shifting. So the Solarc inverter here is able to control the output of 1741 inverters, like those Enphase inverters, by frequency shifting. So you'll notice the frequency of that Solarc will go up when those batteries are full, and up to 63 hertz to shut off that microinverter system. And so it is important when you're sizing your battery bank to a microinverter network like this, that the power that you can charge the battery bank at, and for our batteries, they're all C/2. The power you can charge the battery bank at is at least twice the size, or sorry, the bank capacity is at least twice the size of the power output of the microinverter array. So for example, let's suppose we had 8 kilowatt array on the roof of our house. That means that those microinverters could be pushing up to 8 kilowatts into the batteries if the home is not consuming loads and the batteries are in a state of charge. You would need a battery bank of at least 16 kilowatt hours, because our batteries all charge at C/2 maximum. So you would need a minimum of 16 kilowatt hours. This is a 20 kilowatt hour bank on the screen, so we could do that. And the 8 kilowatt is, of course, the limit of solar input on a Solarc 8.
Yeah. Yeah, right, because we don't have the ability of the charge controllers to curtail that charge rate. One comment here, Nathan, I like that you mentioned that we're bringing in that microinverters into the gen port on the Solar. That's nice because then of course, it limits our ability to integrate a generator, but by bringing it into the gen port, the Solar will display the telemetry or how much power that AC coupled array is producing. We can technically also land that solar on that critical loads panel, right? AC couple on that loads side of things. Say if we did want to use a generator, the problem is that we're going to lose that telemetry. We're not going to know exactly how much solar we're producing because some of that might be consumed by some of the loads in that panel. But either way, and that's the architecture we used on the job I was doing yesterday. We brought that AC coupled solar onto the load center just because it worked a little easier on the house.
Yes, I do want to point out that if we do AC couple on the load side of a solar inverter, you do not have the option of using the generator port. So that is important. You know, don't think that just because you're AC coupling on the load side, you can go and still use the gen port. But Daniel and I will be telling you here in a few minutes that you can integrate generators here with AC coupling, and we're going to talk about it. You can also do both DC and AC solar arrays. So let's suppose you go out to a customer that maybe has that 8 kilowatts of AC coupled solar and N-phase system on the roof, but they've also got a large front yard or maybe another section of their roof, and they say, you know what, I just bought an electric vehicle. I'm upgrading. I want more solar and I want batteries on my house. I want that backup. You can add a DC array in addition to the AC array. And in fact, Solarc recommends you can do up to 19.2 kilowatts of AC coupled solar, but Solarc recommends that you actually have more DC coupled solar than AC. And so we can do both, bringing into, I think it's up to 35 kilowatts on that Solarc 15K that's pictured. And of course, again, we want to make sure that with the AC coupled solar, the battery capacity is large enough to handle the power output of that solar array. So again, we still have a 20 kilowatt hour battery shown there. This is whole home backup in a grid down situation. Same thing, the DC solar is already still alive, but the battery and the inverter are able to grid form, and that'll turn the AC coupled solar on as needed to power the loads and charge the batteries. So this is another example of AC coupling, but we're showing both AC and DC coupling and showing it with a whole home backup with a Solarc 15K. So in a grid down event, the Solarc disconnects itself from the grid. It keeps the whole loads of the house on. And if there's excess solar, it'll allow those batteries to be charged up at the end of the day and used through the night. And when that sun comes back out in the morning, if the grid's still down, hopefully there's enough solar to power those loads and charge that battery back up.
Nathan, we did have a question. James is asking, did I understand correctly that you cannot connect a solar system with an older solar edge? I think maybe a storage system with optimizers to the Briggs battery bank unless you remove the optimizers and replace the inverter. So
you never would. Yes, you cannot. The solar edge inverters are not grid forming inverters. They do not have the ability to DC couple to a battery. We cannot connect our batteries directly to a solar edge inverter. And in fact, solar edge inverters, all these solar edge inverters that you see out there on houses, they do not have they're not grid forming. They do not have the ability to provide backup from a battery.
But we could we not feed the solar edge into the gen port on a Solarc though?
Yes, but I was under the impression that the question was, can we directly connect a solar edge inverter to a Briggs & Stratton battery? And the answer to that question is no. Can we feed a solar edge? Can we AC couple to a solar edge inverter? Absolutely. Through a Solarc inverter or through another inverter, a hybrid inverter of your choice. It just has to be grid forming and capable of accepting AC coupled
like a solar
power. Like a Solarc. A Solarc's a great example, and I'm showing it here, right? So let's suppose that the AC solar inverter on this screen was a solar edge inverter. You would just bring that in through the gen port on the inverter. And that power can be used to charge the batteries in the event of a grid down situation. The SolarArc inverter will grid form, keep that SolarEdge inverter online. Yeah, so SolarEdge inverters have a weird feature to them that they can incorporate batteries to increase self-consumption, but they don't provide any backup power. And I think that that's an unfortunate design flaw with the way SolarEdge has designed their systems, whereas the SolarArc being this hybrid inverter, the grid forming is kind of a much better solution, which is why you can find those secondhand SolarEdge inverters so cheap on the market. I've got one of the 7600s in my garage that was $200. So they don't provide backup power. Okay, so let's take a quick look at a wiring diagram. This is from a SolarArc 15K showing that those microinverters coming in through the gen port on the inverter. And I'm also going to show what this looks like. So the generator port is right here on a SolarArc 15K. Your battery connections are, of course, here on the left side, and you'll want to make sure that you use both of those dual terminals on a SolarArc 15K if you're using a 15K. We do have combiner bars, and we have trainings out there and an integration guide out there to help you navigate the connections here. These are the DC solar inputs, the MPPTs, the 3 independent MPPTs, each having 2 positive and 2 negative connections for paralleling at the inverter. So AC coupling would come through this gen port where the neutral bar is down here in the back bottom. On the SolarArc 15K, we have the CTs. These CTs are going to, any of the SolarArc inverters are going to have these CTs. The CTs are to monitor the power coming from the grid and going out to the loads. We also have these rapid shutdown pins, the BBs that are there, and I'll talk in a minute about connecting a generator. For right now, the connection between the inverter and the battery is fairly simple. You've got your power cable coming out of your battery controller, and then you have a single communications wire for a stack that would run through. We include this blue dongle with the stack controller of the batteries when you buy that. And then there's an additional Ethernet cable that would run into our gateway. And Daniel just went through wiring parallel stacks yesterday. So if you're wiring parallel stacks, it looks something like this. You daisy chain the batteries, you connect the CAN bus output of the first stack to the second stack to the third stack, and then that third stack CAN bus battery channel is going to be running into the SolarArc, and that's what allows the batteries to dictate to the SolarArc how fast they wish to be charged, what their voltage is, all the other information that runs on that CAN bus channel. It's fairly simple in terms of the wiring. Programming here, we're going to get into programming specifically for AC coupling, but you can enter this off the front screen of the inverter, or you can use the My SolarArc app to remotely configure systems. But generally, the first time you install a system, you're going to program off the front screen. It's just a little quicker. And so to get into the programming, you would hit that gear icon in the top right-hand corner. And once you get into the settings, we're going to go into the battery settings tab. So under that battery settings tab, we're going to go to the BAT tab itself. And we want to make sure to check the boxes for BMS lithium battery with the default address of 00 and activate battery tabs, and then click OK to save. Once you've clicked OK to save, as long as your communications are properly there, you should see that battery capacity there. And then the charge and discharge rates you get to set. So those charge and discharge rates are global charge rates. This is solar, DC solar, as well as AC solar, as well as grid. That's the maximum global value. So all charging sources combined. On the charge tab, we will get the option to set that independently. And I want to point out here, especially with AC coupling, how important it is to make sure that you do not exceed the charge limitations of the battery bank. AC coupled systems that AC power is either on or off. And when it's on, the microinverters or the string inverter is pushing as much power as they can. That's the whole job of the inverter, is to maximize the output from that solar array. So we want to make sure that our battery bank, these currents here are DC currents. And so if you want to get a rough idea of how much, how much power is coming out of that, the battery's operating nominally about 50 volts. So if we take the 200 amps times 50 volts, we get a little under 10,000 watts of power. So when you're programming in that maximum charge and discharge rate to the inverter, that's in DC current.
Yeah, and we were working on a system with 9 batteries yesterday, really large, cool system, 585 amps.
There
I
it
will
is,
mention that the most you can
Oh.
set is 275. That would be the limitation on the solar.
And if you parallel multiple solarcs,
Yep.
keep in mind that it's per inverter. So the solarc will only allow you to charge up to 275 amps DC, as Daniel mentioned. But if you have parallel inverters, it's per inverter. So if you wanted to hit, let's say the 585 that Daniel mentioned, the most you could do is 275 is what you would program the master inverter to be. And then it would be double that because you have 2 inverters both kicking out 275.
We get 550 on a
Yeah,
15K.
pretty close. Yes. Okay, and remember what that inverter is doing. It's taking that AC power and converting it. It's converting it to DC and then pushing that into the batteries. And so it needs to use the hardware on the inverter, which is limited to 12K, as Daniel just mentioned, to go between battery and AC, DC and AC. All right, on the battery charge menu, so if you do have AC coupled solar come in, you will use the column on the left for generator charging. That's actually the gen port, also known as the smart load port on a solarc, and you're bringing your AC coupled through that gen port. So you want to have this box checked for gen charging, and you can set the limit to how much charging you will allow the inverter to do off that AC coupled array. And you can set the threshold values, and we'll get into that in the smart load port here in a minute. Under these values on the right side will be set automatically by the BMS and the controller on the inverter. And then if you do want to allow grid charging, this column on the right here dictates the values for grid charging. And discharging values are kind of up to you. It depends a little bit on how frequently you plan to discharge. So if you've got a system that's charging and discharging every day, Daniel and I would generally recommend a shutdown percentage of 20% to get the most number of cycles out of your battery. But for a battery backup system where it's just sitting there topped off waiting for an outage, you might allow this to come all the way down to 0%. So our batteries are warranted all the way down to 0% discharges. Just to extend the lifetime of your batteries, for frequent cycling, we would recommend a 20% reserve. Okay, when we are programming AC coupled solar, we're going to come into the smart load tab under battery setup. So go to settings and then battery setup and smart loads. And you want to make sure you have this box checked for AC coupled solar input to the gen port. And then your customer is going to want to sell any excess. I'm assuming they had an interconnection agreement. So this will keep the AC coupled solar on as long as the grid is on, having this box checked. So want to have that box checked for on grid, always on, unless you have some reason why you don't want that AC coupled solar pumping when the grid is there, then you want to have that box checked. Now, as we mentioned earlier, we don't want to overcharge our batteries, and we cannot slow down the charge rate with AC coupled solar like we can with DC coupled solar. So the best we can do is just shut it off. And so we want to make sure that we shut off battery charging in a grid down event from the AC coupled solar when those batteries are above 90%. And so what this will do is it'll disconnect that AC coupled solar when those batteries are above 90%. But if the on-grid always-on box is checked, as long as the grid's there, the excess charge will flow back to the grid. So we want to make sure that we shut that off at a reasonable value. If you have a very large battery bank that's in a smaller AC coupled array, you could maybe increase that value a bit, up to 95% or so. And then there's a discrepancy between what turns it back on and what turns it off. We're going to let those batteries discharge a little bit before we turn it back on. And so that's why we're down at 80% before we turn the AC coupled solar back on in a grid down event. And that prevents this rapid on-off kind of cycle. Daniel, we have any questions coming?
Yeah, I think I remember looking at this and really, so what it's saying is anytime the battery is below 80%, the AC coupled solar is on.
Yes.
Anytime it goes 90%, it's going to shut off, right? So it has to drop that 10%.
With a qualifier in a grid down situation.
Yeah, that's a good point.
In a grid up situation, so if the grid is there and you have a grid connected system, as you will if you have a grid tied, if you're doing AC coupled solar, right? And you have this box checked, then the AC coupled solar is always on as long as the grid's there. But in a grid down situation, Daniel, you clarified it perfectly. As long as the battery is below 80%, the solar will always be on. And then as that battery starts to fill up and gets above 80%, it's still on until it reaches 90%, and then it would turn off. And that's to just make sure we don't overcharge our batteries. Yep. And with an AC coupled system, you do need to make sure that you have grid cell enabled. You've got to be able to, pass that extra solar back to the grid, because the solar cannot frequency shift if the grid is present, right? So if we've got grid voltage there and grid power there, then that frequency is dictated by the grid. Any other questions, Daniel?
No, keep them coming, please.
Okay, so I'd like to show you, can we do a generator when we've got AC coupled solar? And the answer is yes, especially if you've got a Briggs and Stratton transfer switch. What we can do to prevent the AC coupled solar from backfeeding the generator during a low battery grid down event where the solar has started up the generator and then solar is present, is we can put a lockout module on there. So it is important, the AC coupled solar might see that generator signal as grid presence in a grid down event. And we don't want to backfeed that AC coupled solar into the generator, because we could potentially burn out the controller, right? The alternator there. Okay, so we can put a lockout module on the AC coupled solar, and that just means anytime the generator's on, we can have the AC coupled solar turn off. And as long as the AC coupled solar is producing excess energy in addition to the loads of the house, the batteries should stay charged up, and the generator is not going to start unless those batteries are at a low value, as long as we program it appropriately anyway. So this is a generator we don't expect to do frequent use of, right? Unless it's a really raining conditions or cloudy conditions and the AC coupled solar is not able to charge the battery, well, then the generator could come in. So if you've got long outages, this might be something you want to have as generator backup. And you could also go with a smaller generator here, right, Daniel?
Yeah, as long as it's 240.
As long as it's 240, good. All right, so to hook up the 2-wire start on the generator, you use pins 7 and 8. That's a normally open relay, and when it calls for the generator, it would close those 2 pins, and those are pins 4 and 5 on our generator controllers to enable 2-wire start. What do we also have to do, Daniel, to get the generator to start up?
Yeah, I realize we just got a couple minutes left, but one thing you have to do is program the generator so that if it still sees the presence of grid, which it will if you're microgridding your home, that it can still start up and listen to that 2-wire signal to start. So by default, that setting is not enabled. So you got to get into the controller and change that as well.
Yep, and we give those instructions that are here. And I understand we're almost out of time. I do want to highlight this battery that we've got. So this is our newer battery, 6,000 cycles at a 0.5 C rate, 100% depth of discharge, outdoor rated battery. If you haven't installed one yet, they're remarkably easy to put in. Indoor, outdoor, you can do up to 6 of these stacks. And since I'm about out of time, I'm just going to jump right to the end here and mention our Elite IQ Installer Qualification Program, which Daniel runs. And If you're interested in joining this program, you can get $100 off of each of our batteries that you install. We pay that out quarterly. What else, Daniel?
So we also promote you on our website. We'll put you on our locator maps. We'll send you a little pack, sweaters, gloves, safety glasses. And in addition, there's the ability for us to offer $1,000 off. Now, you don't have to be part of the IQ installers to get $1,000 off your first install. But if you are part of IQ, you will get, in addition to that $1,000, $100 off of every battery you install. Like
So with
Nathan
that
said.
system that you helped an installer put in yesterday, Daniel, they did 9 batteries. They'll get $1,900 back for that system. Yeah,
That's right.
it's a good deal. So wanted to highlight that. Also, if you're here for the NABCEP credits, send an email to energystoragetraining@basco.com. Tell me how you want your name to appear on the certificate. I'll get it out to you. And everybody that attended our training here today will get a copy of these slides. If you have questions, you feel free to reach out to Daniel and I through that email, energystoragetraining@basco.com, or go ahead and give us a call at 805-640-6700, extension 2, to talk to one of our application engineers. Thank you, Daniel.
Thank you, Nathan. Take care, everyone.